Hi, this is now the second video of the tutorial Trees-Based Methods. This is a part of the lecture series Digital Economy and Data Analytics. My name is Eik van Vuren and I would like now to go on with respect to backing. So far we have already been looking at trees, but we now would like to look at backing. Now, a very special thing that we can say about backing is, even though backing is a well-known method in terms of machine learning, we should realize that in sklearn there is no class called backing. And the reason behind that is because of the fact that we should realize that, as already been explained during the lecture series, in fact backing can be seen as a special case of random forest, because of the fact that, at the moment that we're going to do random forest, but the maximum number of features that we're going to have is going to be equal to the total number of features that we have in our data set. So remember that random forest actually allows for a, say, maximum number of features that are going to be sampled from the total set of features. The one thing we can do is that we can simply set the maximum number of features that we can sample equal to the total number of features. Then at that moment in time there is no sampling, of course, because of the fact that this is sampling without replacement. So that implies that at the moment that the maximum number of features is equal to the total number of features, then actually random forest is equal to backing. So therefore what we can do is that we can simply use here random forests and set the maximum number of features equal to the total number of features. Also take into account, by the way, that this is actually the default that we have with respect to random forest. So default in as sklearn, at the moment that you do random forest, you actually do backing. So the question then arises, what do we then have to import? Well, then we have to import from sklearn.ensemble, we have to import the random forest regressor. Again, take into account that this is the easiest way to do it. First of all, because of the fact that then you do not import all other things that are actually from this sklearn ensemble, but it also is nice because of the fact that then you can immediately use this random forest procedure that we have over here. So therefore we simply again have CLF for our algorithm, and then we are going to have random forest regressor, and again we can set the maximum depth thing that we also have to determine over here equal to, random value. Let's start here with 10. And then we can do the fitting process by simply writing down fit, and then we are going to have zlf.fit, and of course, as usual, fitting is going to be on the training sample, so that means that we have to have the x values of our training sample. So we're going to have x train over here. In addition to that, we're going to have y train as the y values of our training sample. Well, then, as usual, we again have to look at cross validation, and then we get a program that looks a lot like what we had with respect to the tree. So again, here we have our imports, and the only difference that we see with respect to the trees that we have seen before is that here we are going to have sklearn ensemble import random forest regressor instead of the trees that we have introduced before. Also, this is almost identical. However, we have here one additional thing, and that is this n estimators. Well, that is the number of bootstrap samples that we are going to take. Take into account that backing means that we're going to do bootstrap samples from, say, the total data set that we have, or the total training data set that we have. The number of times that we are going to have bootstraps, that is in this case equal to this n estimators. And I set it simply equal to 100. That's maybe not that much. We can also set it, of course, equal to 200 or 1000, but the differences usually are not that large at the moment that we're going to do backing. But if you have time enough, then at that moment in time, it might be a good idea to have this number of bootstrap samples a little higher. Take into account that there is, of course, a difference between the number of bootstrap samples and the number of, say, observations that we're going to have in our bootstrap sample, because of the fact that that's always equal to the number of observations that we have in our training sample. Well, then the next things are almost identical. So the first thing that we're going to have is a function which is going to do cross-validation, but this is again exactly identical to what we have seen before, so therefore I'm not going to say too much about it. And also this cross-validation method that we have over here, or function that we have over here, is almost identical to what we had before, with the only difference now that we are going to have here the random forest regressor. And take into account here is that here I do actually have as an additional option this n estimators equal to the n estimators that we have introduced here before. So automatically at the moment that you're going to increase it here, it's also going to be increased in this line that we have over here. And then the rest of it is almost identical, or is in fact identical to what we had already at the moment that we were discussing trees. And that is that we are going to calculate the cross-validation risk. We are going to print it out, of course, and then we are going to, well, store that, and in the end we're going to pick out that, say, depth that is going to give us the lowest, say, cross-validation risk. Well, then also the main file is essentially identical. Here again we are going to have a split between the training and the test sample. Here we're going to get the x and y values with respect to training and the test sample. We're going to do the cross-validation over here, and here we're going to do our, say, we're going to calculate the random forest regressor, but now based on, of course, the optimal depth that we have just calculated. And based on this, we can again calculate the MSE as well as the R squared among the test sample, and we're going to print that out over here in these final lines with respect to the procedure main, and then also we need these final lines that we have over here. If you're going to do that, then at that moment in time we are going to get a test risk equal to 0.0258, and the corresponding R squared in the test sample is going to be equal to 0.9108. So based on this, we are not yet as good as Lasso or Ridge, but we have already done much better comparison to the trees-based methods that, or the trees that we have just seen at in a previous video. Take into account that we can still improve somewhat by increasing the number of bootstrap samples. As I already said, that is standard equal to 100, but based on the on this constant that we have over here, we can increase it a little bit. If we are going to do so, then we can, for example, increase it to 1,000. The difference, as I already said before, is not going to be that big, but we are going to be able to improve a little bit. However, the bad thing with respect to this is that this actually takes quite a bit of time if we are going to increase it from 100 to 1,000. And that's not because of the fact that, doing the backing process itself takes so much time, but doing the cross-validation and doing backing process actually takes quite a lot of time. So therefore, there is an alternative that I also already discussed during the lecture series, and that is by taking so-called out-of-back samples, or these OOB samples that we have over here. Well, if you then are going to look at the total program, well, much of the program is exactly identical as what we have already seen before. However, well, I might even say it's going to be a little simpler because of the fact that the whole, say, function that we had with respect to doing cross-validation, that is no longer necessary because of the fact that we're going to do this OOB, or out-of-back sampling instead. And for that we need to, introduce an option OOB score is going to be true. So that will give us the opportunity to do out-of-back sampling in a random forest regressor, or maybe better to say in a backing setup. Well, then this is exactly the same as what we have already seen before, but calculating the cross-validation risk is going to be now much faster because of the fact that the only thing that we then need to do is that we have to write down CLF, and then we are going to have dot OOB prediction. So these are now going to be the predictions that we are going to have with respect to out-of-back sampling. And take into account that out-of-back sampling means essentially that we are going to use the non-sampled, say, observations. These are going to be predicted in our, say, cross-validation process. Take into account that, well, at the moment that we are going to do bootstrapping, then roughly, well, 30% of the observations are not going to be sampled, and they are going to be used in order to do, say, the cross-validation, in order to predict them in a cross-validation procedure. And, well, take also into account that if we do this, say, 100, or especially at the moment that we do this 1,000 times, then, well, many of the observations that we're going to have, they're going to be not predicted just once, but they're going to be predicted many, many times. And, well, more or less also in 30% of the cases, they are going to be predicted for all the, say, 100 or 1,000 bootstrap samples that we are going to do. Well, what we then are going to do is that we're going to take the average over all those predictions that are going to be made for a particular observation. These are going to be stored into this CLF.OOB prediction at the moment that you do this OOB score that we've over here. And then the only thing that we need to do is then to calculate the mean squared error, which can be done, of course, by using this mean squared error and comparing that with, in fact, the values of our training data set, this Y-train that we have over here. Well, then the rest of it is almost identical. We're going to print the cross-validation risk out, and we're going to choose that, say, depth that is going to give us, say, the lowest cross-validation risk. And also this part over here is exactly identical to what we have seen before. Take into account that here it is not necessary to have this OOB score is true in as an option here. And the reason behind that is, of course, because of the fact that we don't have to do any cross-validation anymore if we already have the optimal depth over here. So in this procedure main, actually nothing is in fact going to change from what we have already seen before. But that also implies, of course, that at the moment that we're going to do this program over here, and we use still n estimators exactly equal to 100, then with respect to the outcomes, nothing is going to change, because of the fact that then what we're going to get in the end is exactly what we have already presented a couple of slides back, namely that the test risk is going to be equal to 0.0258, and the corresponding R squared is going to be equal to 0.9107. So that's exactly the same as what we have seen before. But a nice thing with respect to this is that this goes way faster. And therefore, it is possible to, for example, even if you are still on a little bit of a time restriction, then it is still possible then to set the n estimators not equal to 100, but a little higher, for example, equal to 1,000. Then we get a little lower test risk. The difference is not that big, but we go down from 258 or 0.0258 to 0.0251, and the R squared of the test sample now becomes equal to 0.9130. Again, not exactly equal to what we have seen before with respect to Lazo, but we are going to get a little closer at least.